Okay, data center capacity expanding significantly. I guess in the main, up until recently, at least, it was just the digital infrastructure and applications we all demand, the massive expansion. And one of the consequences of that is much more power needed. So how significant is that power increase just with the digital world? And then I guess we can then go on and find out a bit more about what AI is doing to power demand as well.
Yeah, so has always been significant and will always be significant. But like as you mentioned, the amount of advanced electronics and specifically advanced semiconductors in data centers is exploding. And due to this, there are many new challenges that are becoming, the old challenges are becoming more pronounced right now. First of all, there is the uh, need to actually supply or allocate power to each slot, each rack, each server inside the data center. But since each one is consuming more and more power, it's becoming harder to maintain the optimal performance per component. Therefore, saving power per component is becoming much more of a challenge, much more critical. There are, as always, but again, exasperated, the thermal management complexities, so reliability issues. We're hearing a lot more, perhaps issues that were there academically, but they're becoming a lot more pronounced, a lot more real problems, such as silent data corruption in data centers. So yeah, so reliability is becoming a problem. We can expand on that a little bit later. And then uh, we're seeing a lot more requirements on the regulation part from environmental concerns. So we have to keep that energy consumption lower because we have to meet certain standards currently. So I think those are the three main things that are becoming more and more prominent in the challenges for data centers with the power from the power perspective.
And I guess to make the situation worse, that AI, obviously AI has arrived, but the predictions as to what's going to happen, and I know everyone sort of talks about this mythical 1 megawatt rack that may or may not be sort of somewhere down there. So there's a power problem already, if you like, challenge, but that's going to get significantly worse over the next few years with the amount of AI we're going to see. Is that right?
Yeah, sure. Just check out what Sam Altman said, whether he was serious or not about it, about a million GPUs in the data center. So if you do the math, that would basically mean today you cannot meet those demands. There's no way that could be feasible with the current ability to not even, beyond the financial aspects of it. How do you actually maintain that kind of a setup? From the power perspective, we couldn't possibly, with the given infrastructures and power consumption of such chips, couldn't possibly meet those constraints in this year or in the upcoming years, and therefore really need to have a completely different look, overhaul of the whole power strategy, if you will.
Yeah, and I guess that to the point, there is therefore quite a big opportunity in terms of reducing data center related energy consumption. I know the data centers obviously already focusing on that. But you got any idea of the potential? I mean, we're probably not going to save power because the AI expansion means there is going to be more, but can at least power optimization strategies mean that there is going to be a much less increase in demand than if none of that was done? Is that achievable?
Right. So there's a lot of innovation being poured into power, management, if you will, and but there's always been some kind of, or every age has been a different assumption of it being good enough. So perhaps at the design phase, I'll design the chip to be power aware or power efficient. But then when you get out to production, you're actually produce the actual production of chips yields different variations, and each one has its own specific needs, a different process variation, etc. Different system quality that those chips are integrated into. Later on, there were, developed all the other approaches like dynamic voltage and frequency scaling in order to make sure that you are running at the right frequency per the right workload. So it's customizing the workload or the frequency per workload, and hence by frequency, we're also customizing the voltage and saving power that way. But still, I think the new approach would be to take it one step further and really tailor the power consumption of a component to its actual instantaneous need right now. And I think it's sort of like, think of it as a per chip instantaneous accountability, cutting any kind of guard band to the minimum needed. So I think yes, there would be many new approaches to conserve power. One of them has to be that we can't take overheads just in case. And that was the way things used to work until now.
Yeah, so the world you're describing, I guess, is semiconductors. They're struggling to meet sort of AI demands, and as a result, sort of bleeding energy across the data centers. And yourselves, proteanTecs, you are looking at, if I got it right, AI-driven sort of deep data health and performance monitoring to
Mhm.
help the AI chip makers. And I can't remember what sort of power savings are you potentially helping them to achieve without sacrifice. I mean, because clearly everyone's also worried about performance. So that,
Sure.
yes, conserving energy is great, but if that compromises performance, it's a no-no. So you're helping both power savings and preserving performance. So getting rid of some energy waste in the process. Just, yeah, please tell me a little bit more about the proposition.
Right. So our novel approach is to embed monitors in the chip, and the monitors are aware of the instantaneous power requirement of a chip. Given that we're looking at the performance of the chip and we know how much what the minimum power would be, or minimum voltage in our case, to allow this product to achieve its goals. And at any instance in time, we can adjust that. We have the visibility to see the requirements of the chip and then adjust the voltage to meet that specific demand. So we've been applying this solution to quite a few designs by now, and we're at current count over 100 designs that we're in. And we've seen that this method, this way of looking at what is actually needed instantaneously inside the chip, as opposed to budgeting according to outside sensors, outside pre-planning, has yielded quite significant results. We were seeing with our customers between 8 and 14% of dynamic power savings versus if you were to take a static voltage assigned to each product. And yeah, I think that this is we've been hearing, and this is across multiple verticals, not just AI chips, also telecom, mobile phones, etc. In telecom specifically, we've been seeing those 8 to 14% dynamic power savings.
Okay, and in terms of how the technology works, without obviously giving away your sort of
Yeah.
IP, you're basically then the chips are, I suppose traditionally they would sort of be consuming energy when they weren't needed, firing up a couple of seconds or milliseconds before actually needed, was you're getting it much closer to real time activation of them. Is that the
Yeah.
simple way of explaining it? Is that right?
Yeah, so at the end of the day, a digital component needs to fire off a signal from a source to a sink, and that has to meet timing. So what we call setup timing, or it has to have enough slack. And really, that is the greatest indicator of if this digital component will work. So if it meets its timing requirements, then it will work. And that is heavily influenced by voltage. Okay, the voltage will drive that signal across from source to sink, but also the different factors that affect it during its lifetime may degrade it. For instance, that chip may age over time, requiring more voltage in order to power that same kind of a signal. But not just aging. Aging is a problem that has been addressed in the past. There are different workloads that may be running. One workload would be more challenging than another. There may be V droops, IR drops. There are many, many different challenges, temperature gradients. So there are many challenges that that signal faces to get the timing right. Now, if that chip over time were to exhibit a lighter workload, and perhaps it's a new chip that hasn't been aging, there's no point in supplying it with a very high voltage from day zero. So our monitors that are looking at the critical or the performance limiting paths throughout the chip will note that there's a fair amount of slack and will henceforth recommend a lower voltage. You need a lower voltage to make that to achieve that same performance. However, instantaneously over time, if there was a heavier workload that came in, a burst, for instance, in AI of compute, at that point in time, there would be required more voltage to meet the timing. We would identify this, and this is really where our secret sauce comes into play, the way that we monitor millions of performance limiting paths at system clock level. So there's no loss. Clock by clock, we can note what the real performance is needed. And we can therefore instantaneously adjust the voltage to meet that new demand. So if you think about it over time, we're customizing the voltage to the instantaneous needs of that product with respect to the workloads, the aging, as I mentioned, the different voltage, the power delivery network, the IR drops, temperature, and even, the same chip assembled in two different systems will have two different qualities of power and clock delivery. So we'll take that into account as well.
Yeah, and I'm wondering as well, over time, the work that you're doing, will that have a positive impact on other parts of the chip or even the wider system to help optimize that, because you'll be able to point out inefficiencies or where more power is being supplied than necessary? Is that something that you can help folks with outside of what's going on in the chip itself?
Definitely think about these massive data centers now, especially in with all the explosion of AI, the ability not only to conserve power but to pinpoint the issues that happen, hotspots, V droops, IR drops, etc., is super essential. And doing it in conventional methods is very cumbersome, to say the least. But by having this high coverage spread of monitors throughout a chip would allow a monitoring system to pinpoint a source of, for instance, power consumption, hotspot, etc., very accurately and very specifically. So yeah, that would definitely help in that respect.
And I guess the other thing, I mean, folks are always concerned with the amount of real estate that they're putting on the chip. So you sort of minimize your footprint, and do you draw yourself a minimal amount of power to obviously operate what you're doing? And just describe sort of
Right.
what impact you have on a chip, I suppose.
Right. So we've taken a very conscious design effort because our whole approach is to get high coverage and chip with these monitors, which we call agents. We've taken a very deliberate design approach to make them as least PPA effective, the least PPA effects. So power, performance, area, they have a tiny footprint and their power draw is minimal. So just for sake of getting a picture of what we're drawing on the PPA front, we've never added per design that we're in over between 0.5% and 1% of the gate logic addition, but we've never added area because of the way that we're able to place these monitors in non-congested areas. We've never actually increased the area of a chip or of a block. Of course, if we would have, then we would not be in business, because that is a very sensitive part of for our chip partners. And also from a power consumption, our power addition is minimal. Part of our approach really is to put the minimal necessary monitoring in hardware and have much of the logic of inferring what that hardware says, and of actually producing some insight or action in software that runs on top of it. So all of our solutions are a combination of those hardware monitors and the software, which could be in the form of firmware or embedded software or even cloud analytics that will take the output of these monitors and potentially many of these monitors to have a fair coverage of the chip and to produce, for instance, a recommendation of an optimal voltage or a health score, for instance.
Yeah, and I'm guessing I'm slightly sort of widening out the picture. You're obviously going to contribute directly to less power consumed by the compute, and a benefit for the data center there will be presumably less cooling required. And I know cooling is obviously a very big cost for the data center, and less water. And I know back to sustainability, um, water is quite, is becoming more of a focus of data centers, the amount they consume, etc. So yeah, just give us some idea of the sort of, I suppose, the associated benefits, not the direct ones, but what else you're helping to the data center, minimize, optimize.
Yeah, so definitely cooling is a huge issue. And by reducing the power, we're also reducing the heat and therefore also the cooling requirements. You mentioned also the sustainability aspect of it. So we're helping our customers meet their requirements in that respect. But one thing that we're hearing from some of our customers is extending lifetime as well. So they are less power conscious. Some of these bigger AI companies have a hefty bank account, so they can pretty much foot any bill that's needed, but they want their components to last longer. There's again, going back to Sam Altman trying to produce, eventually getting to 1 million chips, GPUs. It's not that straightforward nowadays to get all those chips out, and we're hearing from many of our customers that they want to actually extend the lifetime of such chips, where once it would have been 3, 4 years and we're switching to a new version. Now they want to extend to 5, 6 years. So one of the side benefits that we're actually from certain customers hearing that is the main benefit is lifetime extension. By lowering the power that is being run over time, the aggregate amount of power, we're actually extending significantly the lifetime of that chip, enabling it to work more in the data center.
And I mean, I've already asked, but in terms of the sort of wider data center supply chain, do you see sort of other ways in which what you're doing can help, different parts of the data center technology stack,
Yeah.
improve their own power efficiency, if you like?
So I will say that I hope this is addressing your question, but I will say that one of the other benefits that this kind of monitoring does that allows the power to always be optimized, specifically the operational voltage to be as low as possible, but still have the product meet its goals, is that the product is more reliable. And the reliability is becoming a much, much bigger issue. Again, looking at the scale of the components, the amount of electronics in a data center, it used to be just put in some redundancy. Nowadays, that's not feasible. It would just be, as is, we're having challenges of getting that amount of electronics in a data center. The fact that we're looking at these circuits from within a chip over time allows us, first of all, like we've been discussing until now, to optimize the voltage, but also to sense when the circuits are degrading to a point of failure before they actually fail. And so it's a double win here. We're saying at this point in time you can afford to go lower in voltage, but on the way we could also say, okay, over time we've noticed a drift, and the margins are getting slimmer and slimmer despite whatever we're doing with the voltage manipulation. At this rate and time, you can expect a failure, and this is super, super critical in data centers because the interdependencies of the different components in the data center and the larger cluster of servers, a failure in one can propagate to many others, which would cause potentially a lot of trouble. For instance, training a model may fail, which is a very, very expensive endeavor. So I'd say that it's a side benefit becoming a major benefit, especially for the biggest of the companies, that we have the unique ability to look at the degradation of a chip from inside over time and signal a potential fault or failure before it actually happens, so that data center is always running up and running without downtime.
Okay, maybe just before we finish, I think I'm right in saying you've fairly recently launched your LVTS solution. Perhaps you can just tell me a little bit about the challenges it's looking to address and obviously how it does so.
Right, our local voltage temperature sensor. So proteanTecs has traditionally provided these monitors that I've been discussing before that we call agents, which are they really feed up into some kind of software stack that would eventually give some kind of insight or action. That being the case, many of our customers are also asking for more traditional sensors to complement their or complement or replace or phase out their current sensing abilities. And our response to that was the LVTS, which is a very small footprint temperature and voltage sensor, about an order of magnitude smaller than the things that are on the market right now. It has the ability to alert on over temperature. It has also the unique ability to be placed in or powered by the digital domain, so by VDD, still being an analog sensor, which means that its placement is much, much easier, much less constraints on, for instance, shielding, etc. It makes it a much more a sensor that is much more easily placed at critical areas inside the chip. On top of that, we have a modularity to that. So it could be the LVTS can be provided as a singular central sensor, a voltage or a temperature sensor. But it also has there's a certain modular option where you can have remote sensors, which are even tinier, placed throughout the chip, all hooked up to that central sensor. Again, that central sensor in the digital domain, thereby giving you like a temperature hub and spoke kind of a infrastructure. So I'd say that our competitive edge is the fact that it is a very small footprint, very easily placeable because of its supply to through the digital domain, and the fact that you can select if you want to have it just monolithic or hub and spoke kind of an architecture, where these spokes are really negligible in size, and you can just place them throughout the chip.
Okay, I mean that's brilliant. And maybe just I'm always greedy, want to know more. So in terms of the roadmap, is there anything you can share? Again, I'm sure the stuff that you're working on that maybe isn't for sort of public consumption, but just give us some idea. Is there more you want to do with what you're already doing? Have you got other sort of ideas? Just anything you can share as to what the future holds for you.
Yeah, we're definitely. The only thing I can share is that we're listening to our customers, and our direction, the roadmap would also on one hand be a more efficient temperature voltage sensor, but mostly we're looking at the solutions needed by our customers. So what are their main problems? And what we tend to do in our roadmap is build the monitors that will feed into a solution that will help our customers with their challenges. So that is how the reliability applications were born. We had the right monitors plus the right software to interpret those monitors to give that health index or that performance index. And we have a few in the roadmap that are addressing other challenges by our customers, but I'm not sure that I can share at this point in time the
No, that's
details.
fair enough. No, I mean, it's been great to chat and thank you so much. I mean, you've explained in great detail what it is you're doing and how you're helping the data. And I do lots of work in the data center industry, so I know just how important power consumption is and optimizing it, reducing it is. So it's been great to hear so many insights and thoughts from yourself, Noam. So appreciate your time. Thanks so much.
Thank you very much. Thank you.